Okay. So we have seen the main theorem, and now we can actually look at some sample cases. So let us look at samples. So I will just give you some eigenvalue maps. The eigenvalue maps will start from the simple ones. If I have a third order system, and if I have this type of set of eigenvalues, we see that they are all in open left half plane. So by using the first part of the theorem, I can actually say that Xe, which is the equilibrium point that this linearized system eigenvalues belong to, is actually locally asymptotically stable. Okay? That is our conclusion based on the Lyapunov's indirect method. The equilibrium point might still be globally asymptotically stable, but we will not know it from the set of eigenvalues or from the linearized system behavior. Okay, so there is no conclusion about global stability whatsoever. Global asymptotic stability. So when I look at another case, I have just this case. In this case, there is again we have a conclusion for the actual nonlinear system equilibrium point. So Xe is unstable in the sense of Lyapunov. Okay. Yes. Şunu söyleyeyim. Şu durum için yazmadık. Yine aynı şey oluyor ama bu durumda there exist eigenvalues on the imaginary axis ama bu durumda unstable dememiz lazım. Değil mi yani? Çünkü sağ tarafta bir şeyler var. Sadece there exist yazıp no conclusion deseydim sadece imaginary eksende olduğunda bu durumu es geçmiş olur. Sağ tarafta yok, imaginary'de var değil mi? Evet. So if we have this case, in this case we see that although there exist eigenvalues on the imaginary axis, this is not a no conclusion case. Okay? In this case we have an eigenvalue in the right half plane, meaning open right half plane, meaning that the equilibrium point is unstable in the sense of Lyapunov. Okay? Existence of the eigenvalues on the imaginary axis does not constitute by itself the no conclusion case. If we have an eigenvalue in the right half plane, we can still conclude instability for the equilibrium point. And finally, let us say we have this case, and in this case we have indeed no conclusion. It really doesn't matter. The multiplicity of the eigenvalues really do not matter. As soon as we have at least one eigenvalue on the imaginary axis, this is no conclusion case. No conclusion using Lyapunov's indirect method. Based on other stuff, you can maybe conclude, but based on other theory, we can conclude, but using Lyapunov's indirect method, there is no conclusion. So now let us visit a physical system that we have seen so far many times. So I will look at the pendulum system once more. The pendulum system has a state, theta and theta dot. And I have the state variables are x1 is theta and x2 is theta dot. So here we have a state equation, x1 dot is equal to x2, x2 dot is equal to minus mgl over j times sine x1 minus b over j x2. Okay? I'm assuming that, of course, b is larger than or equal to 0. Sometimes friction, I can assume that it is 0, and we will investigate the stability of equilibrium points. Equilibrium points that we will consider is the downward equilibrium point, and the second equilibrium point that we will consider is the upward equilibrium point. Okay? We will look at what we can say about the stability of these equilibrium points based on the Lyapunov's indirect method. So here let us quickly find the F matrix that the linearization is going to use. So here del F over del X Jacobian is going to be, I will first write the Jacobian itself only, and I will evaluate it at these two equilibrium points. So del F over del X is going to be 0, 1, and I have minus mgl over j times cosine x1 here, and minus b over j as the last element of the Jacobian. So here, the first thing that I will do is that I will obtain the F matrix for the first equilibrium point. So that is going to be my F1, and I will evaluate this Jacobian at the downward equilibrium point, which is going to give me 0, 1, and at 0 cosine is 1, so I get minus mgl over j here and minus b over j here at these elements. So this is my F1 matrix for the downward equilibrium point. And now let us try to analyze the stability properties of the linearized system. For that, I will calculate Si minus F1 matrix here. That is going to be S and minus 1. And I have S plus B over J. And I have MGL over J. And now I can calculate the characteristic polynomial and the eigenvalues. The characteristic polynomial is going to be d1 of s, let us say. And in this case, it is going to be s squared plus b over js. And I have plus mgl over j. Okay? It is just this characteristic polynomial. And now I can write the eigenvalues. So lambda 1, 2 here is going to be minus b over j minus plus minus square root, I have b over j squared minus 4 mgl over j divided by 2. Okay. In this case, these are the eigenvalues. The first thing that I will do is that I will investigate it using, by assuming that b is equal to 0. Let us assume that there is no friction. If there is no friction, b is equal to 0, and the eigenvalues are going to be given to us as this is going to be 0, and this is going to be 0. So this 2 is going to cancel this 4 here. So the result is actually going to be plus minus square root mgl over j times the complex number j. These are the eigenvalues in this case, when b is equal to 0. So in this case, when I look at the eigenvalue map, I will see the following. Eigenvalues are here and here. So what can we say about the stability of the downward equilibrium point when b is equal to 0? By using Lyapunov's indirect method. No conclusion. Okay? Lyapunov's indirect method gives us, unfortunately, no conclusions using but in reality, what is the stability property of the downward equilibrium point? We know the physics of the actual problem, the downward equilibrium point. Is it stable in the sense of Lyapunov? Yes, it is stable. Is it asymptotically stable? No, it's not asymptotically stable. By using physics, we could understand the stability. But by using only mathematics, by using only linearization, it doesn't tell us anything. Okay? Using linearization does not give us any conclusion. Because we know physics, we can still know the stability property. But this doesn't mean that Lyapunov's indirect method will give us a conclusion. So now assume that B is positive. So suppose that we have friction. B is larger than 0. Okay? I will investigate two different cases. B over J squared minus 4 mgl over J. If this is, let us say, if this is strictly smaller than 0. Okay? In that case, what are the eigenvalues? In that case, I will have lambda 1, 2 is equal to minus B over J plus J times square root 4 mgl over J minus B over J squared. Okay? So in this case, I have these eigenvalues. When the discriminant is smaller than 0, when the quantity in this square root, if it is smaller than 0, then we have these eigenvalues. And we see that both of these eigenvalues would satisfy real part of lambda 1, 2 is going to be strictly smaller than 0. They will be in the open left half plane. Okay? Because they have non-zero complex parts, but the real part is actually in the is negative. Okay? So let us look at this second case. In this case, B over J squared minus 4 mgl over J. Let us look at the case when this is larger than or equal to 0. Okay? In that case, what can I? In this case, I have two complex eigenvalues. And in this case, I have two real eigenvalues. Okay? When I have two real eigenvalues, the question is, can one of them be negative? Okay? So I'm assuming that this number is larger than or equal to 0. This minus B over J is a negative number. Can the addition and subtraction of this thing? Can the addition and the subtraction of this quantity, can it make this negative number positive? That is the question. This is a positive number, so this square root is a positive number. Then I'm adding and subtracting a positive number to a negative number. The question is, can one of the eigenvalues be 0 or positive? What about? So here, what can you say about the magnitudes of B over J and the magnitude of this square root? This is already a positive number, and this is already a positive number. What can you say about the magnitudes of these two? This mgl over J it's always positive. Okay? So what can you say about the magnitudes? This thing is always larger than the other one. Okay? This actually means that addition and subtraction of this positive number can never make this negative number positive. Okay? So that actually means that I have two real eigenvalues and both of them should be negative. Okay? Sometimes they're going to be the same. When this number is equal to 0, they're going to be the same. But I will have two real numbers in the open left half plane. Okay? So in both of these cases, and in this case, lambda 1, 2 will be real, so I can write they are smaller than 0. Okay? I don't have to take the real part anymore. Okay? Because they will be both real. So what can we say? In all of these parts, for both of these two conditions, we have seen that both of the eigenvalues are in the open left half plane. That actually means that if B is positive, I have two eigenvalues in the open left half plane. That actually means that the linearized system is globally asymptotically stable. When linearized system is globally asymptotically stable, by using the Lyapunov's indirect method, I can actually conclude that the actual nonlinear system equilibrium point is locally asymptotically stable. Okay? So XE2, which is pi 0, is locally asymptotically stable. Okay? When B is larger than 0. That is the conclusion of Lyapunov's indirect method. So what can you say about the stability of the lower equilibrium point when there is friction? It is going to be stable, it's going to be asymptotically stable. Is it going to be globally asymptotically stable?
No.
Is it going to be globally? Globally asymptotically stable means that for any initial state, the pendulum should converge to the downward equilibrium point. So the question is, can you find me an initial state for which the pendulum will not converge to the downward equilibrium point? Can you find such an equilibrium point? The upward equilibrium point is such an initial condition. Okay? And actually, if a nonlinear system has multiple equilibrium points, none of those equilibrium points can be globally asymptotically stable. Because if one of them is globally asymptotically stable, then all trajectories should converge to it. But what about starting the system from another equilibrium point? Okay? That means that a system with multiple equilibrium points cannot have globally asymptotically stable equilibrium points. Okay? So here, this is actually the most that we can say here. And in this case, by using the physics of the problem, by knowing that there are additional equilibrium points in the system, we can actually say that it is not globally asymptotically stable. This is not the conclusion of the Lyapunov's indirect method. The Lyapunov's indirect method cannot say anything like this. It's only looking at the equilibrium point locally in a very small neighborhood. Okay? But by using the physics of the problem, we can actually say that this equilibrium point is not globally asymptotically stable. So this conclusion is perfectly correct in that case. Okay? Uh-huh. Hı-hı. Hı-hı. X2'ye geçmedim. Bunun şöyle olması lazım. Yanlış yapıyorum. Yani kafa karıştırıcı şeyler yapıyormuşum gerçekten. Yes, of course. This is the downward.
Biraz saçma olacak ama eğer tepedeki equilibrium olmasaydı sadece alttaki var. Yani fiziksel olarak bir tane equilibrium pointimiz var ama matematiksel olarak bir sürü var.
Doğru.
Şimdi biz yine matematiksel olarak birden fazla olduğu için globally asymptotically stable olamaz mı diyecektim.
Evet. Yani olaya hiç fizik açısından bakmıyorum. Fiziksel açıdan baktığınız zaman global asymptotically stable demeniz lazım. Çünkü o iki equilibrium point aynı equilibrium aslında. Dolayısıyla fiziksel açıdan bakarsam ben buna global asymptotically stable derim. O downward equilibrium point. Aynı yere gidecek yani. 2pi yanındaki yere gidecek. Ama olaya sadece pure matematiksel açıdan yaklaşırsam bir sisteminiz var. Siz sadece o sistemin equilibrium noktalarının yerlerini biliyorsunuz şu şekilde. Periyodik equilibrium noktası var. O zaman ben burada eigenvalue'ları negatif gördükten sonra hala local asymptotically stable diyebileceğim. Ama bunun davranışını fiziksel olarak bununla aynı olduğu hakkında bir fikrim olmadığı için bu sisteme o zaman bu equilibrium noktasına global asymptotically stable değil demem gerekir. Fiziksel gerçeklikten haberim yoksa.
Matematiksel olarak da tek equilibrium point olan nonlinear sistemi
Tanımlayabiliriz.
Öyle bir sistemde linearizasyonda global asymptotic stability çıkarsa nonlinear sistem için global
diyemeyebiliriz. Çünkü şöyle düşünün. Yani bir tane equilibrium point'iniz var. Local asymptotically stable olduğunu buldunuz diyelim. Sistemin periyodik trajektörisi olabilir bir tane. Tamam mı? Yani sadece buna yakın olanlar buna konverge edebilir. Ondan sonra bu arkadaşlar belki şu periyodik trajektöriye konverge ediyorlar. Bundan uzaklaşınca buraya gidip dönüp duracak. Yani tamam mı? Dolayısıyla hala diyemeyebilirsiniz. Tek equilibrium noktası olsa bile global asymptotic stable demeniz mümkün olmayabilir. Ama birden fazla equilibrium noktası olduğu anda demeniz gayet makul. Global asymptotic stable olamaz demeniz. Ama bir tane varsa hala bilinmezlikler dolu problem. If there is, what does it mean for an equilibrium point to be global asymptotic stable? If there exists a single equilibrium point, then I will look at a delta ball around this equilibrium point, and the equilibrium point is going to be locally asymptotically stable if all trajectories started in this delta ball would actually converge to the equilibrium point. Okay, that is local asymptotic stability. For me to be able to call this equilibrium point a globally asymptotically stable equilibrium point, this actually means that I can start the system anywhere, and then the trajectories should converge to the equilibrium point. Okay. Now consider a single equilibrium point and the periodic trajectory of a system. Okay. If I start the system on the periodic trajectory, that is a valid initial condition for me. Okay. If I start the system on the periodic trajectory, then on that periodic trajectory, the system is going to continue forever without converging to the equilibrium point. And that actually means that such system cannot be global, such an equilibrium point cannot really be globally asymptotically stable. So existence of a single locally asymptotically stable equilibrium point does not mean always the global asymptotic stability of the same equilibrium point. Okay? There might be trajectories or other initial conditions. So there might be, for example, some initial conditions where trajectories might be diverging away from the equilibrium point. Even without a periodic trajectory, there can happen such behavior. By using only local asymptotic stability, I know that there is a sufficiently small neighborhood of the equilibrium point where convergence happens. That is what local asymptotic stability means. But we don't know what is going to happen when we get further away from that equilibrium point, and sometimes there might be some initial conditions where divergence might actually happen. In such cases, without even a periodic trajectory, sometimes the single local asymptotically stable equilibrium point might not be sometimes globally asymptotically stable. Okay. Any other questions? So this was the analysis for the. So this is correct, right? So this is local asymptotic stable, and it's not globally asymptotic stable. And this information, not globally asymptotic stable information, came from the physics of the problem, not from the most indirect method. Okay. So here this actually completes the analysis for the first equilibrium point. Now I can go into the second equilibrium point. So xe2 is equal to pi 0. Okay? And in that case, I need to evaluate that matrix at this equilibrium point. Okay? So it is F2. And this F2 is going to be the evaluation of this thing when x1 is pi, when x2 is equal to 0. And when x1 is pi, when x1 is pi, this is going to be minus 1. So the matrix is going to be the following. 0, 1. I have mgl over j, and I have minus b over j. This is my F matrix in this case. And I can look at Si minus F2, and this is going to be S plus B over J, minus 1, and I have minus MGL over J. And now I could calculate the characteristic polynomial of this matrix. So if I calculate the characteristic polynomial, d2 of s is equal to, I can actually write here s squared plus b over j s, and I have minus ngl over j. And I can now look at the eigenvalues. Lambda 1, 2 is equal to minus b over j plus minus square root b over j squared plus 4 mgl over j divided by 2. So now what can you say about the eigenvalues for the second equilibrium point? So here, this number is always positive actually, okay? So this thing is always positive, and it is larger in magnitude than this one, okay? So the eigenvalues, both of the eigenvalues will be real, and furthermore, one of them is going to be positive, and the other one is actually going to be negative, okay? So that means that there exists. So here, if I assume that lambda 1 is smaller than 0, lambda 2 is going to be larger than 0. Okay? And in this case, if we have the eigenvalue map, both of the eigenvalues are real, one of them is positive, and the other one is actually negative. So what is our conclusion? Upward equilibrium point is unstable. XE2 is unstable in the sense of the. So the trajectories, when we get close to it, they tend to diverge in some directions, at least in the state space. So this actually completes the Lyapunov's indirect method. So I will just make a brief introduction. In the remaining time, I will make a very brief introduction to Lyapunov's direct method. We will not learn about the theorems. I will just try to explain the main idea of the method on a simple example. Okay? So let us say Lyapunov's direct method. And in this case, I will just work on a circuit. I have a circuit without even a source here. I have VC, VL, and I have VR here. Here there is a current, and I have IL is equal to IC, and it is equal to IR. This is the circuit of interest. So we have a current-dependent resistor here. So I have R of I is always going to be larger than or equal to 0, or let us say larger than 0, for all i's. Okay? For any current, this R is going to be a positive resistance value. So here I will assume, of course, C and L. They are all positive numbers. So I have L here and I have C. So here the task is investigate the Lyapunov stability of the equilibrium point Xc is equal to 0, 0 of the system using Lyapunov's direct method. In this case, we don't do any linearization. So Lyapunov's indirect method is called like that because we are basing our decisions about the stability of the actual nonlinear system on the linearized system. But here, we won't be obtaining any linearized systems at all. That is why this is called the Lyapunov's direct method. So the first thing that I'm going to do is that I will obtain a state space representation to this system. And I will choose the state vector as the voltage of the capacitor and current of the inductor. Okay? Here, the circuit does not have any source, so the summation of these voltages should be equal to 0. That is what KVL tells to us. So we have VR plus VL plus VC is equal to 0, and KCL tells us IR, IC, IL, they are all equal to each other. Okay, that is what. Now let us write the state equations. So I write C times VC dot is going to be the current on the capacitor. Okay, this is IC. Okay, and I know that IC is equal to IL, so that is going to be my first state equation. C times VC dot is equal to IL. These are all state variables, so my state equation is VC dot is equal to 1 over C IL. This is my first state equation. If I try to write the second state equation, it's going to be L times IL dot. This is going to be the voltage on the inductor. Okay? The voltage on the inductor can be written in terms of the state variables by using these other two quantities. This is minus VR minus VC. VC is a state variable. I don't have to do anything about it, but VR is neither a state variable nor input. So that is why I'm going to replace this as something in terms of the state variables. Okay? Well, this is nothing but the resistor times the current. So it's going to be minus R of IL times IL. So this is resistance times the current on it. That is VR. Okay? Minus VC. So if I write the second state equation, then I could write the following. IL dot is equal to 1 over L times minus R of IL minus VC. So that is my second state variable. So this is the state space representation of this circuit. So here is what Lyapunov's direct. So we would like to investigate the stability of the equilibrium point at the origin. Okay. So we have XC is equal to 0, 0. We see that when I substitute VC is equal to 0, IL is equal to 0. We have IL dot is equal to 0. And we have when IL is equal to 0, VC dot is equal to 0. So an equilibrium point is XE, which is at the origin. Okay. So Lyapunov's direct method would actually try to show the stability of such an equilibrium point by using an auxiliary function. This auxiliary function, for this example, is going to be defined as follows. V of x is equal to 1 over 2 C VC squared plus 1 over 2 L IL squared. I think you can say what this function is. What is it? It's the total energy stored in the system. Okay? So this is the total energy stored in the system. And we see that this is written in terms of the state variables. So this function has some critical properties. And these critical properties are going to be as follows. At 0, at the origin, if I substitute as the x is equal to 0, this function is going to have 0 value. Okay? V of 0 is equal to 0. And this function, if x is not equal to 0, this v of x is always larger than 0 for all x not equal to 0. Okay? I know that for any non-zero x, this function is positive. Okay? And when x is equal to 0, this is 0. Okay? Such a function in function terminology, it is called a positive definite function. this is actually coming even before matrices. Okay? A matrix positive definiteness is actually defined as the positive definiteness of such a function. A is called positive definite when such a function is positive definite. Okay, this is the function positive definiteness, not the matrix positive definiteness. But you can define positive definiteness of a matrix by using the positive definite function definition. All right? Sorry?
They call it positive semi-definite.
Sometimes some functions are called positive semi-definite functions, but this function is positive definite because it is only 0 at 0. If it was 0 somewhere else, for example, this function, v of x is equal to 1 over 2 c vc squared would be a positive semi-definite function because it would be actually 0 not only at the origin, but also whenever vc is equal to 0. This function would be 0 somewhere other than the origin. Okay, that is what would make this function a positive semi-definite function. But positive definiteness requires the function to be 0 only at 0. Okay, at the origin, and this function is what how it behaves. So now I can actually investigate the behavior of this function. If this is my state space, if I have my state space is Vc and IL, this function is actually going to be a ball-like function here. This is v of x here, and it is going to be just looking like this. Okay, so it is a function which is a ball-like structure. It is looking like this, and this is my state space. This is where the state of the system is wandering around. Okay? So if I look at the level sets of this function, or the level curves of this function, they are actually going to be VCIL. They're actually going to be ellipsoids that are looking like this. Okay? So these are the constant v of x line. So if this is v of x is equal to C2, this is v of x is equal to C1, this is v of x is equal to C3 lines. Okay? These lines, as v increases, the level curves of this function would be ellipsoids which have the same center. Okay? That is what we actually have. And here, C1 is smaller than C2 and smaller than C3. And this type of level curves are actually critical for proving stability. Okay? So suppose now that as the system trajectory, if the system trajectory is actually wandering around in the state space, and if I look at the values of v on this curve, okay, on the trajectory at each point in the state space, I can actually evaluate the value of the function v on that trajectory. Okay? So suppose that when I look at these v values on the trajectory of a system, if those v values are strictly decreasing in time, okay? If those values of v on the trajectories of the system, if they are decreasing in time consistently, forever, what can I say about that trajectory? If v is decreasing, in which direction am I moving? I need to be going towards inside, towards the inner level curves here. If v is continuously decreasing here forever, I would actually know that there will be some converging type of behavior towards the equilibrium point. Okay? So that is actually what Lyapunov's direct method is actually going to tell us. It's going to look at whether v is increasing or decreasing on the trajectories of a system. Okay? If they are continuously decreasing, then we will be able to say that the system trajectories are trying to converge to the equilibrium point at the origin. So we are actually going to be calculating V dot here, okay? We will be looking what V dot is. What is the rate of change of V on a trajectory of the system? If this V dot is negative, or if this V dot is smaller than or equal to 0, we will be able to make some conclusions about the stability of the equilibrium point here, okay? If V dot is always non-positive, if I have this case, that is going to mean that the system is either moving towards the equilibrium point, the system trajectory is either moving towards the equilibrium point, or it's moving on one of these level curves. If V is remaining constant, if V dot is 0, in that case, that means that the system trajectory is moving on top of one of these level curves. Okay? If V dot is negative, that actually means that we are moving towards the inner level curves here. Okay? So if V dot is non-positive, we will actually conclude that this equilibrium point is actually a stable one. Okay? So there is no divergence away from the equilibrium point. Remember, stability means intuitively no divergence or non-divergence. And if V dot satisfies this property for all time, we will be able to say that the equilibrium point is actually stable in the sense of Lyapunov. On the other hand, if V dot is actually always smaller than 0, if it is always negative, that is going to mean that the trajectories are always moving towards the equilibrium point. In that case, we will be able to conclude not only the stability, but we will be able to conclude about the asymptotic stability of the equilibrium point. Okay? That is what Lyapunov's direct method is going to be about. So here, we will use such functions, and by using such functions, we are going to be able to conclude about the stability of the equilibrium points. So the first thing that we will do is to learn about the structure of these functions. Positive definiteness, positive semi-definiteness, negative definiteness, negative semi-definiteness. We will learn about those, and then we will be able to apply to see the main theorems about Lyapunov's direct method. That's all for that. Thank you very much.